Okay, let's start with our topic, quantum mechanics, and we will be talking about something known as Zeno's effect. Zeno's effect, and Zeno's effect came from this Greek philosopher, and he is known for the paradoxes. It's one of the paradox, and his name is Zeno. Of course, it's by his name, Zeno of Elia, and again he is famous for his paradoxes, and he is a Greek philosopher. Greek philosopher. Philosopher. Now, I think it's not. It's this because she is philosopher. Philosopher. It's H here. So he is famous for his philosophy, his paradoxes, and the famous one is this Zeno's paradox. Now, what is Zeno's paradox and how is it related to quantum mechanics? So, Zeno says that when we have, let's suppose we have an arrow, we have a target. This is our target. Now, Zeno says that if we have, let's suppose there's a man, someone over here, standing over here, and he shoots an arrow. Okay, he shoots an arrow. Now, moment he release, now arrow is traveling. It will go from here and it will shoot the target, hit. Now, what if as in flight, okay, as in flight, we constantly at every single point of its flight we measure its position. We measure what is it over here, 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 here. We are measuring at every single point during its flight. Now, what's so weird about it, right? Now, Zeno says that at every minute in its flight, our measurement, that arrow is stationary. What he says, it's stationary. It has no change. Meaning, arrow over here, we measure again. We measure again. We measure again. At every point of our measurement, it's stationary. Here it's stationary, here it's stationary, here it's stationary, here it's stationary. So, because of our measurement, that arrow doesn't have motion, no motion or movement. Now, how is that phenomena or the paradox in Zeno that because of the measurement, the arrow doesn't change, doesn't have any motion, it's stationary? How is it related to quantum mechanics? Now, in quantum mechanics, we know that when measurements are made, okay, when we have measurements. Now, what measurements am I talking about? I'm talking about, uh, let's suppose we have a wave, okay, of a particle, and we are not observing it, and it goes through slits, okay. What is this? This is Schrödinger's equation. Sorry, not Schrödinger's, the Young's double slit experiment. Now, this wave goes through here, diffraction happens, Again here diffraction happens, we have a back screen, we get a result, right? Now what if at every point in our experiment, at every point here, let me zoom in here, I observe, this is my point of observation point. What do I see? I see a particle. Again I observe at over here, what I see? I see a particle. Again here here I look at it, it's a particle. Now every point in space I do a measurement, I'm looking at a particle, I'm not looking at a wave. So what's actually happening? I'm stopping the evolution. I'm stopping the evolution. What am I stopping? I'm stopping the evolution of uh, the particle as wave. When I'm measuring it, the wave function breaks, wave function collapses. What do I get? I get a particle. Now it stopped evolving. It's not moving anymore. That's how it is, right? We have a particle, goes here, run this over here, here. It will meet. And at every measurement, I'm stopping its evolution through time. I'm stopping it to evolve. Now that is what Zeno's quantum Zeno effect is. Because of the frequent measurement made in quantum mechanics, what happens is that the mm, evolution or quantum evolution of that particles or that scenario, whatever is happening there, stops. Now, uh, like classically explaining, let me if it like becomes too much of it, let's suppose classically how I will explain is when we look at like a water boiling, when we frequently we keep looking at it, it doesn't boil. It takes time to boil, but when we take our eyes away, it starts boiling. Even though it's not anything, it has nothing to do with your observations. Even if you boil or if you look at it, if you don't look at it, it will boil. But because of your frequent measurements, it feels like it's not boiling. That time you're keeping the passage of time, pass interval of observations short, and that short observation keeps you feel like the water is not boiling. So if that same thing we take it in quantum mechanics, it becomes a paradox, it becomes an effect that because of the every measurement being made in quantum mechanics, we are actually stopping or not stopping, even stopping, we can say, freezing or slowing down the evolution of a particle. Freezing is what we mostly say. Now, uh, one more, uh, one more experiment. Let's do. We have for that we need two things: a, a particle or a qubit. Let's take a qubit because qubit is also a state. It's a particle which we can use in quantum computers. And what we do is that we we make or how about we take a particle? Okay, let's keep it simple. A particle. We take a particle and we keep it somewhere in a box. It's and we cause it to have different spins, spin up or down, or it can be any other diagonal spins as well. By what how can we do this? We can keep a magnetic field in it. We can keep a magnetic field near it. Now, what we do is that these are magnetic fields. Okay, these are magnetic fields, and what happens is we pass the electron particle from here to this whole end of until the end. So what we see, particle is down, we have to bring this particle to an up state from down state. So we have magnetic bars here. Okay, not E, it's B. Now, what happens? It's down, then it's maybe at this angle, then at then maybe it's at this angle, this angle, this angle. Now it's a full up state, full up state, and over here we have a down state and a up state. Now, what if we have something, only one thing, but remember, every magnetic field here is a measurement. Okay, all are measurement. Magnetic field. Now, what if we only add one more thing in this? We add a detector. Now, you might be guessing, what will a detector do in our experiment? What change will it bring? Now, let's look at it. And by the way, all this has been proven. And now, from here till here, what we will observe is that because of the detector, what is detector? Detector makes measurement at every point. Or let's remove this, because here it's not a measurement, actually it's like changing the state every time. But our detector over here, what it does is that it will make measurement on particle at every point after passing through a magnetic field. So what will it do? We're getting a state, it goes to again same state, again then again same state, then again. We're actually limiting, we're slowing down, we're slowing it down, but again it also means that we're actually stopping it to change its state. At first we gone from down state to up state, but now because of frequent measurement, the particle doesn't change its state and it remains in the same state. Okay, means it will remain in the same state as it started from. We are, because of the gain and frequent measurements, we are stopping that evolution. That's what we call evolution. Okay, evolve. We're stopping it from evolving. So that is quantum Zeno effect. And what is actually happening is that particles probability is getting 1 minus t over a certain equation. You don't have to know about what this equation does, but just let it be in your mind that at first, if the particle is in this initial state, it will remain in the same state, or we're slowing the rate at which it's going to evolve. Now, there's an opposite thing as well to it. There's something known as anti-Zeno effect. Anti-Zeno effect. Now, what is anti-Zeno effect? This is the last thing we will talk about. So this Zeno effect is, we have our, let's bring Schrödinger's cat into our phenomena, into our equation. Now, what's so special about Schrödinger's cat? We have a cat, and again, poor cat, it's going to die. Now, if we do the same experiment in which we keep a bomb, okay, we keep a bomb, and it has a 50-50 chance of exploding. But what we do is that uh, we keep on observing. Now again and again we will open the box, again and again, or many times we will open the box and do measurement, or frequently is much better scientific word, frequently uh, observe. Now What will happen? Our observation will, we will have the slowing of the slow rate of it exploding. This explosion rate will slow down. Or let's add a poison which can decay. It's much better. Decay will makes it much better sense. So let's pause. We will slow the decay rate of the. We will stop the decay, or we will stop the evolution of decay. But anti-Zeno effect shows that it can also affect the decay rate as well. We can actually cause, because of our observation, we can actually cause for the cat to die fast. That's anti-Zeno effect. Because of the anti-Zeno effect, it can also happen that we are the cause of this cat's death before it should have happened. We have increased the rate. Increase the rate. That's anti-Zeno effect. Because of our frequent measurements, we actually cause for a cat to die before it could have been killed. Before that, the decay of this poison, or this decay of this atom, which is radiation, of course. Radiation. Now, that's what Zeno effect is. Anti-Zeno effect. Zeno effect shows our measurement. There are many applications as well, and there's one more about the transition of in a transition of particles from one state to another. And because of the frequent Zone effect, we get some states in which it goes, which shouldn't it in which it shouldn't be. And anti-Zone effect shows that it will also have many other modes as well, many other transitions as well. So if there's Zeno effect, there's anti-Zeno effect as well, and because of them, we can actually increase the rate. Yeah, thank you.